As the name implies, two-dimensional NMR experiments produce results that have two separate frequency, or chemical shift axes. This video is meant to give a general description on how these experiments work and how to use Topspin to display and manipulate datasets. To get a better understanding of these techniques, we first need to present some concepts of the simple one-dimensional experiment and how it can be manipulated into giving 2D results. NMR data is collected with experiments that are called pulse sequences. The simplest sequence that is used for routine 1D NMR experiments is the single pulse experiment shown here. The relaxation delay is a period of time that allows the nuclear spins to reach their equilibrium state. This is followed by a very short radio frequency pulse that excites the spins. The resulting free induction decay is then collected during the acquisition time. For proton experiments, the default relaxation delay is usually set to 1 second, while the acquisition time varies on the facility's instruments from 3 to 5 seconds. The pulse width is usually described by the resulting orientation of the nuclear spin's magnetic vector. Maximum detected signal results with a 90-degree pulse width. The time needed for this is usually around 10 microseconds. This has to be carefully calibrated on each instrument for each nucleus. On our Bruker systems, the parameters Topspin uses for these values are shown here. Most 1D experiments are run with pulse widths less than 90 degrees to allow more efficient return to equilibrium. A 30-degree pulse is used in the pulse sequence called ZG30. Signal to noise is improved by signal averaging the FID. This is accomplished by rerunning the pulse sequence multiple times set by the parameter ns. Remember that signal to noise scales with the square root of the number of scans. The FID is a time-based measurement that includes all of the frequencies of the NMR spectrum. The frequencies are extracted from the time-based data with a mathematical operation called the Fourier transform. The result is a frequency-based spectrum that the software can either display in Hertz or convert to a parts per million scale. The FID is sampled at discrete points over the acquisition time. The spacing between data points is called the dwell time. The resulting frequency span or spectrum width is set by the reciprocal of the dwell time. The spacing between the points in the resulting spectrum is called the digital resolution. This is determined by the reciprocal of the acquisition time. So, for one-dimensional results, a single time domain is transformed into a single frequency domain. Therefore, for two-dimensional results there needs to be two separate time domains to generate two separate frequency domains. How is the second time domain generated? To answer this question, let's look at a generalized scheme for two-dimensional pulse sequences. There are 4 elements that each 2D sequence contains. The preparation and mixing periods can be composed of pulses, or pulses separated by fixed time delays. During these periods, magnetization is prepared and transferred between interacting nuclei. Separating these two periods is a varying period called the evolution time. Standard conventions labels this as time domain 1. This is what we would consider the additional time domain needed for two frequency dimensions. FIDs are collected in the detection period at each discrete value for T1. This acquisition time is labeled as time domain 2. During the evolution time, peaks in the resulting one-dimensional spectra generated by time domain 2 show modulation based on their chemical shifts. This is called chemical shift encoding. These peaks are also modulated by the interaction produced by the preparation stage. For all 2D experiments, the parameters of the T1 time domain defines the resulting F1 frequency domain just as the FID time domain parameters defines a one-dimensional spectrum. The spacing between the discrete time increments of T1 will set the spectrum width. The length of the longest T1 delay will set the digital resolution. Since the increment of each T1 value is usually constant, the number of collected spectra will define the F1 resolution. In Topspin this is set by the TD parameter. 2D results are usually shown as a contour map. The two frequency axes form a plane. NMR signals are displayed as contours much like a topographical map. Rings of the contour slice through the peak and get smaller as the height of the peak naturally tapers. We will get a better view of this a little later. Let's take a look at the simplest two-dimensional pulse sequence where the preparation and mixing time are a single 90-degree pulse. This sequence is called the Cozy experiment, which stands for correlation spectroscopy. While there are many variants to the Cozy experiment, the basic two-pulse experiment is still very common and often mistakenly referred to as the one and only 2D NMR experiment. As we will see with later videos in this series, there are a tremendous variety of 2D NMR experiments, and these can be classified in a couple of ways. We can group these experiments by either having a single or different nucleus on each axis. We could also group experiments by the type of NMR interactions that is being exploited. The most common nuclear interaction that 2D NMR experiments manipulate are the spin-spin coupling that causes the multiplets in NMR spectra. This interaction is transmitted through chemical bonds. Therefore, it can be used to show molecular connectivity. The Cozy experiment is the most common homo-nuclear experiment that uses spin-spin coupling. However, there are many more. The Topspin experiment gives results similar to the Cozy, but it extends the correlations over all protons in a spin system, not just close neighbors. Since carbon-13 natural abundance is so low, special experiments have been developed to detect interactions between directly bonded carbons. The inadequate pulse sequence is the most common, but these experiments still suffer from low sensitivity and usually require very concentrated samples and are not commonly run. Heteronuclear spin-spin coupling is exploited in several very useful experiments. Generally, these experiments include proton and one other lower frequency nucleus like carbon-13, nitrogen-15 or phosphorus-31. They are broken into two sub-classes based on which nucleus is detected in F2. The directly detected experiments collect data on the lower frequency nucleus and were historically developed first. However, since these nuclei are less sensitive than proton, they always take much more time to collect. The indirectly detected experiments, that detect signals from the protons, have become the standard way of running heteronuclear experiments that correlate through bond interactions. The more common examples include the HSQC and HMQC pulse sequences. These experiments correlate nuclei across a single bond. The other commonly run is the HMBC experiment that correlates nuclei across multiple bonds. Through space interactions are more commonly performed with homonuclear experiments that detect protons. These include the NOSY and ROSY experiments. The heteronuclear experiments are very difficult to run and are rarely useful. There are some 2D experiments that do not fit well into these categories. Here are some of the more common examples. J spectroscopy shows the coupling multiplicities along the F1 axis. There are homo and heteronuclear versions, but neither are run very often. The XC pulse sequence is the same as the NOSY experiment. However, the correlations are due to slow chemical exchange between two chemical shifts and not a through-space interaction. The DOSY experiment measures diffusion coefficients. It is not truly a 2D NMR experiment. The second axis shows the diffusion coefficient that is mathematically extracted from a series of 1D results. Now let's move to Topspin, where we have loaded a 2D Cozy spectrum. We will review how to collect and interpret these results in the next video. Here we will show you some features of the data and how to manipulate it in Topspin. The dataset shown has a 13.7 ppm spectrum window in both dimensions. This corresponds to about 5500 Hz on a 400 MHz instrument. The T1 domain was collected with 128 increments. We can view these FIDs with the FID tab in the data window. Topspin includes all the FIDs into a single series file. If we expand into the series, we can see the individual FIDs that will be processed into 128 individual 1D spectra. The T2 FIDs were each collected with 2048 points. This gave an acquisition time of about 0.19 seconds. This is a lot shorter than the typical 1D experiment that has an acquisition time of about 3 to 5 seconds. 2D experiments are usually run with limited f2 resolution to save on computer file size and processing time. Even with this short T2 size, it is about 20 times the length of the T1 domain size, which was about 0.012 seconds. The resulting digital resolution in f2 is about 5 Hz. This is more than enough to resolve chemical shifts for most spectra. The f1 resolution is larger than 80 Hz, which is 0.2 ppm on the 400. Keeping the total experiment time short is the reason for this limited resolution. This experiment took 10 minutes to run. To achieve the same resolution in both axes we would have to collect 16 times more increments and the experiment would take more than 2.5 hours. The difference in resolution in the two axes can be seen in the projection on the f1 versus the f2 axis. Also notice that the contours are stretched oblong in the f1 dimension. Still, this resolution is usually enough for most spectra since the added second dimension reduces possible overlap. This 2D dataset is the result after Fourier transformation in both dimensions. We perform this double transformation with a single topspin command. However, this operation is actually a three-step process. To demonstrate these steps, we can transform just the T2 FIDs. This shows the individual 1D spectra and how the data looks before the second transformation. At the top is a projection of all the individual increments. This represents a low-resolution 1D spectrum of the sample. Note the streaks under each peak and how they appear broken. This is from the intensity modulation that is produced by the different T1 delays of the pulse sequence. We can use multi-display mode to show the modulation on each peak. Notice how the frequency increases the further the chemical shift is from the center. These modulating signals are similar to those seen in a one-dimensional FID. The vertical running slices, called interferograms, are generated from every data point in the f2 dimension in a process called transposing. The full dataset is then Fourier transformed to give the resulting 2D spectrum. Typically, these datasets are shown as contour maps. Like a topographical map, the rings in the peaks denote an amplitude. Taller or more intense peaks will have more rings. The peaks in the spectrum can be shown with a pseudo-stacked display. Notice how the peaks have shapes similar to a 1D spectrum. Let's go back into the contour display and look at some of the controls in Topspin. The data is always shown with the f2 dimension running along the horizontal axis and the f1 dimension running vertically. The button bar is slightly different than what is shown when a 1D spectrum is open in the data window. However, many of the buttons are the same and they perform similar functions as they do with 1D results. Here are some of the more important ways to interact with 2D spectra in Topspin. The mouse moves a cursor that has two lines running along both the f2 and the f1 axes. The top left corner will show the coordinates of the cursor with the spectrum intensity at that point. Chemical shift expansions can be made with the mouse by moving the cursor to the point you want to start the expansion. Click and hold the left mouse button and then move the cursor to the other end of the region you want to zoom in to. Note that when you move the mouse, a box is created showing the final region. Release the left mouse button and the display will update with the zoomed region. There are several buttons to perform expansions. Like with 1D spectra, only one is really useful. The exact zoom button, with the ppm icon, will open a dialog box that has the two ends for the zoom region for both the f2 and f1 axes. Enter the desired values and click OK to update the display. These two buttons will bring back the full spectrum on either the f2 or f1 axis. Click on this button to display the full spectrum in both f2 and f1 dimensions. The button with the return icon will bring back the last expansion. Just like with 1D spectra, the height of the peaks can be controlled by rotating the mouse scroll wheel. Note that you can lower the peak height below the threshold on the lowest contour and the peak will disappear from view. Likewise, you can increase the height so much that the noise floor is above the lowest contour and fills the display. The multiply and divide by buttons can also be used to adjust the peak heights and they work like they do with 1D spectra. The spacing and number of contours can be controlled by the Edit Contours button. This dialog box has several ways of controlling the contours. The easiest to work with is at the bottom. The base level does not need to be changed. To get contour rings that are spaced closer, use a smaller number in the level increment row. The number of levels can be increased to make sure the top of peaks are mapped with contours. After changes are made, you need to click on the fill and then the apply buttons before the display updates. Note: these adjustments are cosmetic and reversible, so feel free to adjust these settings to determine the best combination. The defaults left by Icon NMR processing usually have large spacings with too few levels. The best contour settings could be different depending on spectrum type, the displayed chemical shift scale and the peak widths. Also note that this only controls the interactive display in Topspin. The plot editor will have similar control for output that is separate of these controls. When you are satisfied with the contour spacing, exit the panel with the OK button. The vertical heights of the projections can be adjusted by first clicking into the region to make it active. Notice that the small square above the projection becomes filled when selected. Now the mouse scroll wheel, or the vertical scaling buttons will work on the projection. You have to activate each projection separately. It is important to note that both projections can be active at the same time. Also note that you have to click on each to deselect them before you regain control on the 2D contour region. This dataset is shown with the shadow projection on the F2 and F1 axes. When 2D experiments are processed with the automation, the projections will be replaced by true 1D spectra. You can manually replace the projection by right-clicking in the projection area to display a pop-up menu. The internal projection option is the shadow projection shown here. Choosing the external projection option will bring up a dialog box where you can enter the file name and experiment number for the 1D spectrum. For homonuclear experiments, both axes need to be defined separately. Right-clicking in the contour display area brings up a different pop-up menu. Here you can access many of the main button options. The more useful controls are toggling the projection display. This will hide the projections and make the contour area fill the display. The other is the square display toggle. When off, the contour area is expanded to fit the full data window. The square layout gives a more logical representation of the spectrum when you are working with a homonuclear experiment with the same chemical shift expansion in both dimensions. However, neither option is wrong, and this is just a cosmetic choice for viewing the results. This concludes our introduction on two-dimensional NMR experiments and how to manipulate them in Topspin. The next video will show you how this cozy dataset was collected, what the peaks represent and how to interpret the results. Please see the staff if you have any questions about 2D experiments and how to work with them in Topspin. Thanks for watching.